And it's time for Module 12. Dr. Ron Eglin again. And what is Module 12? We've looked at regression analysis, one dependent variable, but multiple regression analysis allows for multiple independent variables with one dependent variable. And it's common. It's not like it doesn't happen. It happens quite a bit. So let's talk a little bit about this. Okay. In the case of this, the model is expressed in very similar to the previous model. The y equals beta naught, that's your intercept, plus beta 1 times x1, plus beta 2 times x2, plus beta 3 times, and it can go up as many. Lots of betas, lots of independent variables. So what do we want to do? Well, what we really want to do is we want to calculate those betas, but we also want to know if the fit is good. And there's a lot of gotchas in multiple regression. So we got to look at those gotchas. Now, I'm not going to have you doing any complex multiple regressions in this class, but you need to be aware of what multiple regression is and what it does and what the gotchas are. So this is used everywhere, all the way from sales to medicine to engineering. What multiple factors affect an outcome? And in most cases, it's not just one input that affects an outcome. It is multiples. So before we were using some squared errors, we are now using ordinary least squares. Now, all I'm going to say about this is it's a different mathematical prediction technique to find the values of the beta naught, beta 1, beta 2. Okay, it is actually beyond the scope of this class, but there are actually more than one parameter estimation method, but OLS is typically the one that's used for calculating that simple linear format of the equations. Now, there's actually some complications that you can have that we'll talk a tiny bit about later on, because it doesn't necessarily have to be that y equals, beta naught times x1, beta 1 times x1, beta 2 times x2, beta 3 times x3. Those can be a little bit more complex, but this is the method. Now, first you got to know what the coefficients mean. Well, the intercept is just that. It is the intercept. It's where where if all the values of all the actual independent variables are 0, it intersects the y-axis, which would be the value of the dependent variable. Now, so that's what the coefficients really represent the magnitude of change with each of the independent variables has on the dependent variable. That should pretty much make sense. And there's different ways of assessing this. So the t-test is typically considered the standard by which looking to see if there is a statistically significant relationship with the dependent variable for any given independent variable. But it's a little bit more complex because when you're dealing with multiple independent variables, what you typically do is just like, well, which one is actually have an effect? And then you got to deal with multicollinearity, and that's really where I'm going to concentrate a lot of what I'm going to talk about here. So an example, simple example, if you're trying to predict home prices. Well, home prices can't really be predicted by one thing. Square foot to price is one thing, but you've also got other factors: amount of land, 1-story, 2-story, number of bedrooms, number of bathrooms. Now, some of those may have collinearity. Now, the example I'm going to give you for collinearity is a little bit more obvious because I'm going to go through an example here. But realize that you've got multiple variables that can come up as part of that prediction. Now, how do you do this? Well, one of the things that you can do is forward selection and backwards elimination, where you basically start with whatever variable you think is going to be the most significant predictor, and you do a model. That's it. And then you think, well, let's add a second independent variable and add that to the model. And then you can go backwards by pulling some out. Now, does that mean you have to go through and calculate one at a time? No, there's actually built into Python the method of going through and doing that. So you can use the methods that are built into the statistics models in Python, noting that this is the methodology that you use. And it could give you different answers using different methodologies, just so you know. Now, most of the time, what I am typically doing is what I call stepwise regression, where I actually go, I put a variable in, I put another variable in, I've checked to see that that variable, whether that variable that I'm adding has a collinearity with a variable that I've got in the model already, to see if it actually has an effect of being able to explain more of the variance, decide whether that is actually useful to have in the model, and then I may go backwards from there. So just one at a time, checking multicollinearity of each one, which right now I haven't done a great job of defining multicollinearity. It's coming up. So I came up with I thought was a good example. So one of the metrics that you can use to figure out how good it fits, R squared. But typically with R squared, every time you add an independent variable, you get a slightly better fit. So it basically says, I'm going to add more variables until I get the best fit possible, but that's not necessarily the best model, because you're adding complexity to the model every time you add a variable. So there's an adjusted R squared, which is basically modifying the R squared so that every time you add a new variable, you add a penalty, and that penalty may offset the advantage that you get by adding another variable. The root mean squared errors is another one. And in this case, the root mean squared error is a low value is good. And there's other criteria like the how to pronounce the AIC and the BI. The BIC is easy, the Bayesian Information Criterion. But the cake information criteria is another one. And those, I'm not going to show you the calculations. I just want you to know that there exists criteria, that you're not just blindly saying, I think this is the best fit. You can actually calculate criteria that you can add. And again, this is something that you're going to do in Python if you're going to do it, or you're going to actually have that calculated, and then evaluate using those specific criteria as you go. The best model is going to be the one that explains the variance in it the best, but you want to actually not introduce extra variables that you just simply don't add anything to the model. So one of the things that you can do in the feature selection is look at the F-scores, which you can do. I've actually got the code snippet to do this right here. And it's in scikit-learn, and it calculates the F statistic and the p-values. It's and then you can look at these and say if it's a more efficient regression model. So, and typically when you do that, you are going to get a more efficient. Now, that's kind of beyond where we're planning on going in the class itself. The important piece that I'm going to talk about now is this. If you're going to be doing this, you need to look at the biggest effect that you're going to be dealing with when doing a multivariate analysis with multivariate regression is going to be multicollinearity. And what that really means is when you're adding these variables, two variables that you add that are independent variables can be so closely correlated that you really only need one of the two. You may get a better fit for the model, but you've added complexity without adding really anything into the fit itself. So one of the things that you can do is you can look at the variance inflation factor. And that's actually relatively easy to do. You can create a correlation matrix, which is also really easy to do. And you can actually do a plot of the correlation of all the different variables that you have. And that's built into Seaborn, which is one of the statistics libraries. I think it's the Seaborn plot has that plot built into it that gives you the ability to actually do a correlation matrix with plots of all the values versus all the other values. So typically one that I would say you should be able to do is, well, you should be able to create a correlation matrix. That's not very difficult to do because you're just saying, I got 5 variables. I'm going to have 5 different variables on one axis, 5 different variables on the other axis. I'm going to have I'm going to have 25 plots because I'm going to have all of them across. But reality is the plot of something versus itself makes no sense. So you've got 25 minus 5, so you've got 20 plots. Of which are correlating every variable with every other variable in the model. I actually did the example I did, I think has 5. And the variance inflation factor gives you a number that actually looks at, the number gets bigger the more multicollinearity you have. So typically you're going to set the cutoff for VIF around 10. If it's higher than 10, the variable is highly VIF. And the reality is it's going to be correlated with another variable in the model, maybe more than one, but it's going to be correlated with at least one other variable. And it really says is you don't need both of them to get a good model. And here's the code, the simple code to be able to create a VIF table is here. You just look for the function is variance inflation factor. And you can just look at it for every single one in the model itself. I'm going to actually give you an example of this. This is a pretty good example here. This is what I came up with. Let's see. You can't read the bottom of that. Let's go up a little touch. All right. Predicting the price of a used car. And let's say we've got the variables that we want to look at: mileage, age, engine size, horsepower, number of previous owners. Okay. And those are what we're going to say. We're going to predict the price of a used car based on those. But I want you to think about this. Mileage and age. I'm going to just guess that mileage and age are going to be correlated. I don't know that yet because I haven't gone through another analysis, but I'm also going to guess that engine size and horsepower are also pretty heavily correlated, and that the numbers of previous owners probably has no correlation with engine size or horsepower, but it may have a correlation with mileage or age. Don't know. So on that case, but we don't know any of these at first. So what I could do is I can simply plot. I think there's a correlation between age and mileage and engine size and horsepower. And if I plot them against each other, I'm looking at that going, there is a pretty strong correlation between age and mileage and engine size and horsepower. I mean, it's pretty obvious that there is a correlation there, and that would definitely say that you're going to have a high level of multicollinearity in the model itself. Now, if I were to calculate the VIF, the inflation factor here, and I say in this case, I'm just going to say anything over 5. I'm going to use really low criteria. Well, look at mileage, age, engine size, and horsepower. Well, the mileage and age, 219, which shows actually kind of says, oh, you know what? That's probably where that correlation lives. And engine size and horsepower, and those are pretty close together, saying maybe that's where that correlation lives because those numbers are similar. It doesn't mean they are because it could just be by chance. But if you look at the top, the VIF at the top, you see that number of previous owners, 3.83. Well, that's below 5. It doesn't look like it correlates very heavily with anything else in the model. So what can you do in here? Well, it doesn't mean you're going to throw out mileage, age, engine size, and horsepower, but the reality is you probably don't need mileage and age, and you don't need engine size and horsepower. So what you would do is you could do previous owners with horsepower and age, horsepower and mileage, engine size and age, and engine size and mileage, and look to see which of them gives you the best model. Each of them having 3 rather than 5 independent variables. That's what you would do. And it's not that hard to do to get that good model that way. So, and I'm not going to spend, as you can see, I'm kind of going to zoom through this. So if you understood the last one, we were talking about 1, well, now we're just talking about 5 independent variables trying to figure out the model. And you're looking at that beta naught. Again, standard linear, the big challenge here is most of the time it isn't beta naught times x. It might be beta naught times e to the minus x or something like that, which is a little bit more complicated. That the variables may not be just beta times x. Also, There's another one where you've got beta times, you have a beta times x1 and x2. That's a different model altogether too. But realize that when you're talking about multiple independent variables, there's a lot of different forms that the equation could take. So how do you address the multicollinearity? You can remove some of the variables. That's really the bottom line for the big thing. There are other methods of getting and reducing that. And again, because we're not going to be dealing a whole lot with this, it isn't really, and I know if I cover it in the lecture, you're just going to glaze over anyway. But one of the ways that we deal with this many times is we look at other variables and look at variables that might not have that correlation effect that goes with it. Because if you look at my example, it was pretty obvious that you were going to have a correlation between mileage and age and engine size and horsepower. I mean, that just doesn't, those are, anybody who knows cars knows that would probably exist. So what can you do when you get beyond linearity? There's this whole field of polynomial regression, fits nonlinear relationships. But again, what I want you to understand is that there are all sorts of forms of equations where you've got many where you've got, say you've got 7, 8, 10, 20 independent variables. It can be a ton of them, and you want to come up with the best fit possible. And as you get bigger and bigger and bigger, you start getting into all sorts of things like weather prediction and other things where there's lots of variables that you can input into the system. Okay, and once you throw in spatial analysis piece, it becomes even more complex. But we're not going to go any more complex than just that. My example with the cars. That's as far as we are going to even look at it. And there, guess what? Python has all the sklearn libraries have got polynomial features if you need to do it. And if you're doing that, you're probably going to be moving upwards into graduate level programs where you're going to be doing it for specific scenarios, specific situations. There's a lot. I'm not going to go through all the different ways that you apply polynomial regression, but you can read these. It's also something that you're going to research a lot more if you plan on doing this. With any multiple regression technique, you've got the same challenges you had in linear, but you've also got a real risk of what we call overfitting. You can, like high degree polynomials, often you can get a really good fit when you're doing the actual fitting, and then you come back and you start testing it against field data that you've just collected, and you're like, oh, that didn't work. So, and then you've also got extrapolation. Even if with the standard single dependent variable, extrapolation is always a danger. And in multiple, when you're dealing with these, it gets even more complex. And the computations, some of the mathematical techniques for computing the factors can take a while. That's not been as bad. I mean, back when we actually were doing this on x86 processors, you would go, that's probably not practical to even try to do some of these more advanced models. And now they probably are much more practical. There's a lot of different types of validation techniques. And this is actually kind of getting now when we talk about even the AI, where you've got training and testing techniques where you use one set of data to train into a model and you use another set of data to test the model itself. There's a lot of different types of cross-validation techniques that you can do, and a lot of different ways to do residual analysis. And then you might come up with a lot of different predictive models that you need to compare against each other. And so again, this is just so you know it exists. You're not going to do this in this class, so that you know. But I do want you to know that it's out there. And in this case, the workflows, I do want you to kind of have an idea of the workflows, because in this type of model, the data preparation, the building, and the validation being totally separate pieces, So as you prepare the data and you look at what you're going to put into your model, you put your model together and then you validate it. And all that occurs. There are each of those is its own step. It takes that you're going to put a lot of work into. And then the final deployment of a model is, and what I really want you to think about in this case is something like a hurricane predictive model. You train hurricane models on a ton of past data, and then you select a specific, you come up with what you're going to actually put into that model. Those are mathematical models. You see them on TV, and then you validate it to say, hey, here's, I've got these hurricanes that I trained it on with the input parameters that I had, and then I'm going to now do these other hurricanes that I didn't use in the build model, where I actually found the factors, the predictive factors that I was, the betas basically, and I'm going to validate it against other things, and then you put it out there, and it's actually a fairly significant deployment too, because they're fairly complex models. So what are we going to do? Well, I might give you a really simple problem when you identify a multicollinearity, and that one might be it for the class. There is a lot, and this is an entire. Well, actually, give you multiple regression. Actually, pretty much single linear regression, single regression with single independent dependent also can get fairly significantly complicated when you get into it. But multiple really can get. There's multiple classes in statistics at the graduate level you would take to go into this, and so again, it's about knowing that there are ways to do this. And if you need to learn them, you're going to go and take the classes that you need to learn them. I know this because I did all those classes when I was doing my dissertation. I took a ton of statistics classes to be able to develop the models that I needed to develop. But that actually were, and they were predictive models for doing things. I mean, I was predicting pollutant loads in stream flow based on upstream inputs, and it was an insanely complex. It was volumes of data that I worked with. So, just an interesting thing. I don't want to get this to get too long. If you do have questions about this, I think you've got enough to be able to do what you need to do. And I'm very enthusiastic. You guys, the group that I have, at least this semester, because you're probably watching this has done a good job. They've understood what we're talking about here. So that's it. Thanks.